Okay, we're going to take a look at game theory in this part 2 video of aggression, conflict alliances, and conflict resolution. So let me get to my PowerPoint slide, get to where I need to be. I think it's this one. It isn't this one. Okay. We're right here. Sorry about that. So when we talk about conflicts over food or territory or mates, when animals have these conflicts, the question is, well, actually, there are a lot of questions that we might have. When should an animal actually fight for a mate or a territory or food? If they fight, how long should they fight before they give up? What are the costs of fighting? How can animals maximize their fitness during periods of conflict? In other words, an animal wants to maximize its ability to survive and reproduce. That's our understanding of evolutionary theory. And so when it comes to conflicts over food or territory or mates, how does an animal know what to do? So that it can maximize its ability to survive and reproduce. Well, game theory is really comes out of mathematics. It's a branch of mathematics that is used in a lot of different fields, but it can help us answer questions about animal conflict, and it can help us predict how animals are going to behave in different situations of conflict. And so animal behaviorists use game theory regularly to help make predictions about what animals should do to maximize their fitness. And game theory then assumes that animals are going to act to maximize their survivorship and their reproductive success, to maximize their fitness. That's an assumption of game theory, all of the game theory that's used in animal behavior. And so we can say that game theory is used to study the evolution of behavior when an individual's fitness depends upon his own behavior and the behavior of others. Oh yeah. Think about conflict for a minute. Conflict happens when an animal engages in the conflict. An animal has its own behavior, but it also has the unpredictable nature of the other animals that it's fighting against. And that makes it a little bit harder to predict, right? Well, game theory helps us to predict what animals should do in different situations. One of the simplest types of games that game theorists have come up with is called the hawk-dove game. It doesn't have, we don't need to think about hawks and doves in the game, but those are just two terms that are used to describe the players in this game. It's a simple game that's used to predict animal behavior during conflict. And what it's going to do is it's going to pay attention to the costs of fighting, the benefits of fighting, and the different strategies that are used in the population and how common they are. So the basic model goes something like this. There's a contest there's a resource out there that is contested. Maybe the resource is food, maybe it's shelter or territory, maybe it's a mate. And V will equal victory, the benefit of victory, or the value of the resource that you're fighting for. Okay? There is a cost of fighting. Sometimes we call it injury, the injury cost, or I. And for animals who decide not to fight, but instead to display, like to do a threat behavior, if you will, that cost of displaying will be D. And there's two strategies in the hawk-dove game. Just two simple strategies. You can either be a hawk or you can be a dove. A hawk is a player that fights either until it has the resource or it's injured. It doesn't bother making threat displays. It just fights until it has the resource or until it's injured. A dove is a little more complicated. A dove player will always flee from a hawk. First of all, a dove will never fight. It will flee from the hawk. When it sees another dove, it will display to the dove. And when it flees from the hawk, it loses the resource. It never wins. When it displays to another dove, it tends to win the resource on average about half the time. Okay, now we need to think about the payoffs, the payoff matrix, if you will. I have to let in my dog, so hang tight. Okay, so this is a kind of chart that you're going to see when we talk about game theory in general, these kinds of payoff matrices. And what we've got on the top of this chart is the opponent. Okay, the opponent can either be a hawk or a dove. You are the challenger. You can either play the role of hawk or dove. Now, when an opponent is a hawk and the challenger is a hawk, the payoff when a hawk fights a hawk is this. Yeah. About on average, a hawk fighting another hawk will win the resource about half the time, and about half the time lose the contest and incur an injury. So the total payoff then would be half the value of the resource minus half the cost of the injury. If the challenger is a hawk and it's fighting a dove, or and it's playing against a dove, it will always win. It wins the whole resource. Okay. The dove, on the other hand, sadly, doesn't fight, doesn't incur an injury, but it doesn't fight, doesn't display, it just gets 0. Okay, now as a challenger, you can also be a dove. When a dove takes on a hawk as the opponent, it flees. It incurs no cost, but it also doesn't get the reward. The hawk gets all of the resource, right? When a dove takes on another dove, on average, it wins the resource about half the time, but there is a cost of display. So minus the cost of display. Half the value of the resource minus the cost of display. Okay, so now the question is, what strategy should the challenger use? Okay. Which strategy should the challenger use? Well, it probably depends upon a variety of things. Let's see. Let's think about these questions. What strategy should the animals use? Should this animal be a hawk or be a dove? When is it best to be a hawk? When is it best to be a dove? Does the cost of fighting or the value of the resource affect which strategy to use? Clearly, in all of these games, and in the hawk-dove game, the animal is trying to maximize its fitness. So what strategy should the animal use to maximize its fitness? Let's take a look at an example that you're going to be going through from Simutext. This is from the assignment that you'll be doing called Playing Games. And I've got it open. The Playing Games assignment, it has 23 so-called pages, and you're going to be moving through these pages. I want to get to page 10 or so. 9 or 10 is fine. And I want to talk about the example in and kind of play with the example in this Simutext. I like it. So the example in Simutext that focuses on the hawk-dove game is all about pikas. Pikas are these cute little rodent-like animals that live in really high elevations in the mountains, and so you can see them if you go to like the Rocky Mountains, Rocky Mountain National Park or Glacier National Park. You'll see them. They hibernate in the winter, and then all summer they have little territories, and they gather hay and they make hay piles. And occasionally they fight over their territories and they fight for those hay piles. Well, we're having trouble with my dog today. He's staying after this. Okay. So the question is, when two animals are contesting a territory, should they fight or not, right? That's the question. Well, we have to know a little bit about the average payoffs, if you will. And if you look to the right-hand side, we're not even really going to focus on this left-hand side. We're only going to focus on the right-hand side, okay? If you look at the bottom right, there's a cost benefit and an average payoff here, all right? So what this simulation does is you can change the costs and the benefits, and that affects the average payoffs. And then we can ask the question, what's the best strategy to be if you're the challenger? If you're challenging an opponent, should you be a hawk? Should you be a dove? Which is the best strategy under different conditions? So here's one situation. Suppose the benefit of victory is very high relative to the cost of injury. So I'm going to slide my benefit of victory to the highest I can make it, 100 units of benefit. So you're going to win a lot of hay piles, I guess. The cost of injury, let's say, is really low. Like maybe these animals don't really fight aggressively at all. And the cost of display, I'll just leave it at 10. The cost of losing is 0. You don't, there's no, let's not worry about that. And so what the payoffs did was it essentially did exactly like we've sorted out in our payoff matrix on our PowerPoint slide. So if you're a hawk fighting a hawk, challenging a hawk, the benefit is 30. A hawk challenging a dove is 100. A dove challenging a hawk is 0, and a dove challenging a dove is 40 on average, right? So if the benefit of the resource, the value of the resource is really high, what do you think what strategy should you take on? Should you take on a hawk strategy? Should you take on a dove strategy? Well, let's check out what would happen if we had a whole group of doves, like 999 of them, and one hawk. What would happen over time? Would the doves become fixed in the population, or would the hawks increase in number because of this payoff matrix? So what I'm going to do is I'm going to click go, if you will. Whoa. Over at about 25 generations into this game, it looks like all of the members of the population are hawks. It pays off to be a hawk in this game, it looks like. In fact, there are no doves after 25 generations. They're just gone. It's better to be a hawk. Why is that? The payoff is always greater to be a hawk in this case. So in this case, a hawk can invade a population of doves, and the payoff is always better to be a hawk. When the value of the resource is high and the cost of injury is low, it's smarter to play the strategy of hawk all the time. This is called an evolutionarily stable strategy, when one strategy is the best strategy and it can be invaded, if you will. And this is typical of a situation in which the benefit of the the value of the resource is really high and the cost of injury is really low. It's worth being a hawk, okay? Because the hawk against hawk is better than the dove against hawk. The hawk against dove is better than the dove against dove, okay? The row here, the hawk row for the challenger, is higher than the dove row. So we find that in this situation, when V is much greater than I, when the benefit of the victory is much greater than the cost of injury, it tends to pay off to be a hawk. But what if we change this around a little bit? What if the value of the resource is much lower and the cost of injury is much higher? Okay, now take a look at our, so what I did was I just flip-flopped these. Now take a look at the average payoffs. And this time, it's not a big, you don't gain a lot from the resource, but you do lose a lot if you get injured, right? In this case, on average, when a hawk challenges a hawk, there's a negative 50 payoff. Ooh, fighting is bad. When a hawk challenges a dove, the hawk wins and gains 20 points, 20 whatever points. A dove against a hawk, it turns out to be 0, and a dove against a dove turns out to be 0. All right, what's going to happen in this situation? Are doves going to kind of take over? Are hawks going to take over? Or are we going to reach a kind of an evolutionarily stable equilibrium where we've got both strategies that kind of stabilize in the population? So I'm going to click reset and click 100 generations. Go. Oh boy, look what happens in this situation. If the cost of injury is high, and especially relative to the value of the resource, it looks like we reach an evolutionarily stable strategy that is a mixed evolutionary stable strategy, composed of 2 strategies that are in a stable equilibrium. So we see an increase in doves initially, and that stabilizes. We see an increase in hawks initially, that stabilizes. We see a decrease in doves, and that stabilizes. In this situation, it might be best to be rare. So when there aren't very many hawks initially, you're going to do well against the population because most of the time, as a challenger, if you're a hawk and there's almost all doves around, then you're going to win. You're going to do really well. But what if it's the opposite? Most of the population are hawks. If most of the population are hawks, you probably don't want to play a hawk because you're going to lose all the time. So when most of the populations are hawks, let's reset this and hit go, then it pays off initially to be a dove in that population. But we still reach that evolutionarily stable strategy or equilibrium, a mixed evolutionary stable strategy, if you will. And so this just gives us an idea of how we can predict how animals are going to behave in a conflict. And the rest of the Simutext playing games simulation will go through different kinds of games, maybe more complex games, different examples of animals that whose behavior is predicted by the hawk-dove game or by other evolutionary games that people have come up with. So it's kind of an interesting simulation, and it helps us understand and predict the behavior of animals during conflicts. And that's it for this video.